A fluid is any matter that has tendency to flow. All liquids and gases are together referred to as fluids. Solids and liquids have a fixed volume, while volume of a gas depends on the volume of its container. However, when an external force acts on certain categories of bodies, their volume changes and the bodies develop a restoring force. The restoring force acting per unit area is called stress. Change in volume due to stress is negligible in solid, very small in liquids, and very large in a gas. Liquids are 10 to the power 5 times less compressible than gases, but are about 10 times more compressible than solids. This is because the molecules in a liquid are not as closely packed as in a solid, but are closer to each other as compared to a gas. Another common physical quantity related to fluids is pressure. Pressure is defined as force exerted per unit area. We experience so many incidents involving pressure in our day-to-day life. One such example is that it is easy to drive a sharp nail into a wall than a blunt one. This is because, for a sharp nail, the area on which force acts is less, hence, more pressure. Here, the force exerted on the nail is perpendicular to the surface on which it is applied. Similarly, the force exerted by a fluid on an object submerged in it is always perpendicular to the object's surface at all points. This is because if there were a force parallel to the surface of the object, then, according to Newton's third law of motion, the object would resist the force in the opposite direction, which would cause motion of the fluid along the surface of the object. However, the fluid is at rest. Since there is no flow of fluid parallel to the surface of the object, we can conclude that the force exerted by the fluid at rest is not parallel but normal to the surface of the object at all points. The normal force exerted by the fluid at a point can be measured by the device as shown in figure. It consists of an evacuated chamber with a spring that is calibrated to measure the force acting on the piston. The inward force exerted by the fluid on the piston is balanced by the outward force due to the compression of the spring, which is measured by this device when placed inside the fluid. Let us now learn how to determine pressure. If F is the magnitude of the normal force acting on the piston of area A, then the average pressure, PAV, is defined as the normal force acting per unit area. In limiting case, that is, if small area of the piston is considered arbitrarily, then the pressure is represented as P is equal to delta F by delta A as delta A approaches to 0. The magnitude of pressure does not change with direction. Hence, pressure is a scalar quantity. Dimensional formula of pressure is the ratio of dimensional formula of force to that of area. Dimensional formula of force is mLT power minus 2. Dimensional formula of area is L power 2. Hence, dimensional formula of pressure is mL power minus 1 T power minus 2. Similarly, the SI unit of pressure is the ratio of SI units of force to that of area, which is Newton per meter square, which is also referred to as Pascal or PA. Pressure is commonly expressed in atmosphere, symbolically written as ATM. Atmosphere is defined as the pressure exerted by the atmosphere at sea level, which is equal to 1.013 multiplied by 10 raised to the power 5 pascals. Another important physical quantity related to fluids is density. Density is represented by Greek letter rho. Density of a substance gives a fair idea of its heaviness. It is defined as mass per unit volume. Density of a fluid of mass m occupying volume v is represented as the ratio of m to v. As mass and volume both are scalars, density is scalar and its dimensions are ml power minus 3. In SI system, density is measured in kilograms per cubic meter. Density of a liquid is almost considered constant at all pressures, as it is largely incompressible. However, gases exhibit huge variations in the densities at different pressures, as they are compressible. As it is not always possible to remember the density of materials with their true units, generally we refer to relative density. Relative density is the ratio of density of the substance to the density of water at 4 degrees Celsius. For example, relative density of aluminium is 2.7. Relative density is a scalar quantity. It does not have units as it is the ratio of similar quantities and thus it is a dimensionless quantity. The pressure on an object submerged in a liquid is independent of the area of cross-section. Consider a liquid in a cylindrical container. Now, consider a cylindrical element of the liquid with base area A and height h. In it, let mg be the weight of the cylindrical element. Let 1 and 2 be points on the flat surfaces of the element at its top and bottom. The force due to the liquid pressure on the top surface of the fluid element is P1A, acting in the downward direction, while at the bottom it is force P2A acting in the upward direction. Then, since the liquid element is static, the net force acting on the element in the vertically upward direction should be equal to the weight of the element. But the mass of the cylinder is equal to the product of its density, ρ, and its volume, V, or the product of its density, ρ, area of its base, A, and its height, h. Substituting equation 2 in equation 1, we get P2 minus P1 is equal to rho Hg. Thus, the pressure exerted by a liquid column of height h is independent of area of cross-section. The liquid also experiences pressure on its free surface. This pressure exerted by the atmosphere is called atmospheric pressure, is denoted by Pa. If point 1 of the liquid element considered is on the top surface of the liquid and is exposed to the atmosphere, then the pressure at the bottom of the element becomes P equals Pa plus rho Hg, where Pa is atmospheric pressure. Here, the pressure difference, P minus Pa, is called the gauge pressure at that point. This gauge pressure thus depends on the density of the liquid, the height of the liquid column, and the acceleration due to gravity at the given place. Thus, at a given height, the gauge pressure is the same at all points at the horizontal level. Let us consider an activity that confirms this concept. Consider various vessels of different areas of cross-sections connected at the bottom by a horizontal pipe. When a liquid is poured through the opening of a vessel, we observe that the liquid occupies the same level in all the attached containers. The level of liquids, H, in all the containers is the same though they contain different volumes of liquid. This proves that the liquid pressure is the same at all points at the same horizontal level or depth.